All right, so these are our gas laws, right? This is pressure. This is force. This is area, right? So a 1 Pascal, right, is a Newton per square meter. So this is a tremendously small unit of pressure. Remember that it takes 1.013 times 10 to the fifth pascals just to equal an atmosphere, 14.7 psi, which is an atmosphere, right? So in some ways, psi is a better unit here for us, right? This is the moles, right? Right. This is number of particles, literally the number of particles. This is a tremendous number, right? And then this is Avogadro's number, right? Uh, 6.02 times 10 to the 23rd. Right? Another way to calculate N is, of course, it's the grams you have divided by the molar mass. Okay. Yeah. Okay. And then here is our ideal gas law, right? We'll talk about the one with Boltzmann's constant here in a second, right? So that's our ideal gas law. If I rearrange this, I get that PV over NT is equal to R, and R is a constant, right? So really, you can add the number of moles there, but I don't think they're going to change the number of moles on you. So this is the combined gas law, right? And I wrote problems that use this, but I don't think they're going to change the number of moles on you, right? And then take a look at this, right? So somehow NR is equal to the number of particles times Boltzmann's constant, right? Right? Whoops. And then I think that's because Boltzmann's constant is equal to R divided by Avogadro's number. Does that work? I think it does, right? Because if I just go N times R over NA, right, I get nRT, right? Yeah, there we go. So Boltzmann's constant is actually just the ideal gas law constant divided by Avogadro's number, right? And this is a really small number, okay? So if you had the number of particles, you could use Boltzmann's constant. And then, of course, all these temperatures have to be kelvins. Okay, so if they give you degrees Celsius, remember to add the 273, okay? Ta-da, ta-da, right, there it is. I'll cast that one out there all day long, right? Okay, so make sure you use kelvins. Do not use degrees Celsius, okay? Because, of course, you could easily have 0 Celsius. It's just the freezing point of water, and then we'd have infinity right here, Okay, this is another pressure one. This one's in terms of the density and the velocity and the RMS velocity, I'm sure, right? Okay. And then down here, this is the internal energy of a gas. Okay. Wingy. Right. So this U is the aggregate. Oops, we need a couple. Aggregate energy of the gas. Okay, it's the total internal energy. So 3/2 nRT. This is, of course, T in kelvins, right? Okay. And then in terms of the number of particles and Boltzmann's constant, there it is, right? Okay. You're going to use this one more often, I feel like, but there it is. And then I think I did a physics problem of the week last year. You can see I think Ben Nickel derived this from just momentum and stuff, which is kind of cool. Kind of makes sense. This is a new formula here, so I guess look for that. We didn't really do that last year. I don't think there's anything else to say about this.